This one is an interesting proposal by Google to circumvent an attack called DNS Cache Poisoning. You might say, didn't we fix this DNS cache poisoning with DNS over TLS and DNS over HTTPS? Yes, we kind of did, right? But the problem is adoption. It's always slow to adopt new technology. Right? We always know that introducing a new thing takes time. Look at IPv6, right? Although it's been introduced decades ago, I think, it's not yet fully adopted in the internet, right? It's being adopted, but it's not. It's very slow to adopt a new thing. But here is, we need to talk about a clever way, might I say, that Google introduced through a paper. This is the detailed paper, and I'm going to reference it below. And this is their proposal draft RFC. So they're going all the way and actually submitting an RFC. Look at this. This is not something new. This was introduced back in 2008, and just now it became a reality. So let's start with the problem, right? We can read the abstract a little bit here. This actually gives a little bit more flavor of what the problem is, and then we can dive into these things, right? Let's get started. Abstract. We described a novel, practical, and simple technique to make DNS queries more resistant to poisoning attack. Mix the upper and lowercase spelling of the domain name in the query fortuitously. Almost all DNS authority servers preserve the mixed case encoding of the query in the answer messages. So you see, when you make a DNS query, says, okay, example.com, the client-side library that you use probably is going to send it in whatever the author of the code sent that URL to be. Like if you said it, usually it's always lowercase, right? www.example.com. And you want to make a GET request. Internally, you don't even feel it. Your fetch, your Axios, your Python request library, your anything will have to do a DNS query, right? In order to find the IP address to make a TCP connection, right? Because you can't do anything without it. Connection, right? You have to have a connection to do a thing. But in that thing, you're sending an actual DNS query, and that DNS query that looks like I want to www.example.com. The servers will actually preserve whatever casing you have. If you ask for all caps, it will return, say, this is what you asked for, and this is the IP address, right? And it doesn't really matter if you're asking for example.com all caps or example.lowercase, the lookup on the, the zone files, like think of it like almost like a database lookup, is case insensitive. But the return type is case sensitive. It will, whatever you request, is going to reply back with the same exact casing. And that is the key for this paper to work. If this was not the case, this whole thing is going to be tossed, right? There are still some DNS server that doesn't comply with that, right? But that's what it is, basically, right? So fortuitously, almost all DNS servers preserve the mixed case encoding of the query in the answer messages. Attackers hoping to poison a DNS cache must therefore guess the mixed case encoding of the query, and that's their trick here, right? In addition to all other fields required by the DNS poisoning to work. This increases the difficulty of attack. So what we're doing here is just increasing the difficulty of attack. So what we're gonna go here in this paper, I'll go through the diagram here. You can go ahead and read this, but I'll explain everything in this beautiful diagram that they did here, right? So let's talk about cache poisoning first. What is cache poisoning? By the way, I'm going to reference a video I did about DNS. If you don't know anything about DNS, check that video out. I'll talk about that in details. And in the podcast, I'll also reference that in the podcast show note. I have a podcast on the same thing. My videos mostly are podcasts, because thing. Right? So a stub resolver, or just sometimes called a resolver, right, is the one that makes the request. There is something behind this guy, which is your client library, right? Yeah. So what is calling, what we're seeing here is a query for google.com, right? Give me the DNS IP address, the A record, as they say, for google.com. What we're showing here is what is happening in the backend, the real backend. You know, when you make a request to like an Axios or Fetch to fetch something from a page, the first thing that this library does is a DNS resolution. And you're right here, somewhere here. I think you can see the mouse, right? You're somewhere here. And this is where like you're going to talk to your local DNS recursor, right? This could be your router. Mostly it's your router, like your local DNS is your router, or whatever the router is configured your DNS to be. Sometimes when you do a DHCP, the DHCP will return the DNS server to you as you assign your local IP address, right? And that's when you find out your DNS server, your recursor. That could be 8888 Google or 1111 Cloudflare or any other. Your ISP could have a DNS recursor, right? And those recursor will just talk to the resolver. And they're kind of the same thing, right? These resolvers, this is what we're talking about here. So your router sometimes will do the resolver, sometimes it will just forward it, sometimes it will just forward it to an upstream resolver or a stub resolver. Sometimes they call it recursor. And now we're truly in the backend here, right? So now the google.com query now will turn around, and the stub resolver which is just merely forwarding the request to an actual recursive DNS. This is the guy who actually does the work, right? So these resolvers, which could be your ISP or any other DNS recursors, will forward the request to an actual recursive DNS server that actually does the work, right? This guy doesn't know much. Doesn't know how to do the DNS resolution. This is where I talked about DNS in details. They talk to the top level domain, and then, okay, they start breaking up the queries. Like, oh, what is it? Oh, you were going to the .com? Let me get the .com server. And then, oh, let me get the google.com. Where's google.com? Who's the authority? Who's the SOA, right? Let's start off authority. Who's the authoritative name server? And then give me the google.com. Right? So we're taking the last possible step here. We already did the top level domain, we found the top TLD server, we found the authoritative name server, and now the recursive DNS is talking to that. It's sending a query, looks like that. Although there is an ID, the query ID of the DNS, because DNS is stateless, well, DUDP is stateless, which is what DNS is built on top. You need to include the request ID with every diagram you send, because when you get back, how do you know that, oh, this response is for this request? You need something to match. We don't have this problem with TCP, with a full state connection, because whatever we send, we're going to get back on the same connection, right? On the same port, right? So we don't have this kind of problem. And even that, really, we have to identify requests sometimes, right? Or you have to do it the HTTP way. It was like, okay, you send one request and you got to wait on that connection until something you get back on that connection. And that is gotta be the response for the request you just sent. Otherwise, you have to implement pipelining, the ordering of the request, and it's gonna become very complex, you know. Streams in HTTP 2 and 3 kind of solve this problem, so that we can kind of tag almost each request with a stream ID, so that we send a request in a stream, and we know that this is whatever we get back will be whatever we sent. Right? All right, long story short, we need to send a stateless parameter such that to identify things. I mean, we do this with REST all the time, right? That's why REST is called state transfer. So we send the ID. That will tell us exactly when we send this 93 ID, we're going to give it back and it says, okay, I got an answer. The ID is this. And this is what you asked for. Look, same casing, google.com. And this is the IP address for google.com. Here's what a nasty attacker would do. It will say, okay, I have no idea what do I know? I know that this is using the recursive DNS using UDP. So if I can guess the ID, which is really a 16-bit, I think, integer. So they will just gonna slam every possible combination. Hey, attacker will just say, oh, just flooding A responses to the recursive DNS, assuming it doesn't even know that's an ongoing request is going. It says, hey, Google, by the way, google.com is this. Google.com is this. Google.com is that. And we'll try. Here's the ID. Here's the ID. Here's the ID. If the ID matches, then the recursive DNS will be poisoned with a wrong answer. If it happened to be arrived before that answer, and this is the graph they show. It's like the distance really matter here, right? So if the attacker managed to respond right before the SOA, the authoritative server actually respond, and they match the same ID, you got poisoned. Now, what's the problem with this? The problem with this is not that easy, right? Because we actually have other parameters to protect us again. Because why? This was easy maybe 20 years ago, because we always used port 53 for DNS. Like, oh, if you know port 53 and this is port 53, then the attacker, the datagram will go destinated to port 53, and the recursive DNS, of course, the recursive DNS server, you know it, so you send it, and the matching, the UDP datagram will arrive immediately, will of course passes the kernel, and says, oh, the kernel actually, oh, I have a kind of a, not really a listener, but a socket attached to this port, so let me forward this UDP to the application, which is the recursive DNS, and that packet will go to the DNS, right? And then the DNS will start peeling the data and says, oh, the ID is wrong, I'm going to discard it. Okay? Then, until the ID matches, then we get poisoned. And that's the problem. It doesn't really take much to solve this. So what I think a researcher called Kaminsky, if I'm not mistaken, it came up with the idea of randomize the port. It was like, let's make the ports random so that the guess became harder. Even that didn't really solve much, because like the port is like 16-bit, right? so that's not much either. So the guess started a little bit harder, but with a lot of compute, you can still poison a specific domain. So hey, I want to poison google.com. I'm gonna flood a recursive DNS with this answer, with this IDs, and at some point, by the way, the ID was actually incremental, which was a bad idea. Someone from the dev team says, like, you know what, guys, let's randomize the IDs. Imagine, yeah, things were really bad 20 years ago, you know, but now it's so much, much better. So the IDs are randomized, so the guessing is harder. The ports are randomized, the guessing slightly harder, not hard enough though. I suppose what the attacker need also to do is to spoof the source IP address to effectively claim to be the SOA, right? Spoofing is not easy, by the way. Like spoofing an IP packet. I mean, you have to write custom stuff to do this stuff, right? It's not like you're going to send requests from, you're going to poison from your own laptop. Your ISP won't let you, because it will say, wait a minute, you're trying to send an IP packet from that's a source IP doesn't match yours. What are you doing? The ISP will just actually drop it. So it's like, come on, I'm not going to let you do that. That's not your IP address. You're lying. You're spoofing. So most ISPs actually do that, right? So this attacker should be really sophisticated, maybe to own their own ISP, or to be really bypassing the ISP in a way such that don't have that stuff. But yeah, in a nutshell, that's what's the cache poisoning is, right? So what Google came out was like, okay, since we know that if we send google.com, we're going to get back google.com, let's play with the casing so that we're adding another harder way to figure out for the attacker to make a guess. So this time, if the recursive receives a google.com normal request, the recursive DNS was going to change it to www capital G small o capital O G L0 capital LE and .com. Even that is, mixed casing. And then we're going to send that, and the SOA will reply with exactly that. 99% according to Google. Most resolvers and authoritative name server will just take whatever is in the packet and will reply back. Luckily, because we have really good programmers back in the day, I'm not sure about these days now, they wrote an optimization such that this is happening. This is a kind of side effect of an optimization, where when a datagram is arrived, that space is just really reused. That same memory location, they say, okay, I'm just going to take that memory location. I'm not going to create a new packet per se. I'm just going to say, okay, because the response is really very similar to the request. This is the same. The ID is the same. So I'm just going to add additional stuff. So that's the same memory allocation. So that is why we get the same result. This is as opposed of creating a new malloc and then copying the memory, the data from this and this, and then replying with it. That's an additional work that you don't have to do if the response is identical to the request. That's a very clever way of optimization. That's a low level thing, right? Does it have to be in a low level language to do that, I suppose, right? All right, so that's very interesting. I love this stuff. So how do they actually do the casing? This is where we go and learn about something called bit 20 or bit really 32 in decimal, right? You see, ASCII is interesting. Let's go to ASCII. Let's go do some JavaScripty thingy here. So if I do capital A dot char code at, I think 0, do we see what we get? This is the coded value, ASCII code for the letter A. If I do a.char code at 0, it's 97. So the lowercase a is higher than uppercase a. And do you know what's really the difference between these guys? Right? It's actually a single bit. So let's do 65. Notice how 65 looks like, right? Let's copy it right here. And then notice how 97 looks like. Did you see that? The difference is a single bit. And this bit is called bit hex 20 or bit literally 32 because 2 to power what? 5? The 5th bit, right? What you need to do to capitalize is just literally flip that bit. And all of a sudden, you change the lowercase. So if you flip that bit from 0 to 1, it becomes a lowercase. If you flip it from 1 to 0, it becomes an uppercase. And that's the whole trick to this thing. So they have what they do is they flip these bits, right? Even flipping these bits is not as simple as you might think. It's not as straightforward, let's say, right? So they have also the algorithm right here. So let's read the algorithm. If the jth bit of 0 make the I character uppercase, so they change it, like they OR it, or they AND it. So they can literally flip the bit, right? That's how they flip it. But how do you actually do it randomly? So when I first read this, I was like, okay, oh, that's nice. That's all I know. But then they actually went above and beyond. No, those guys actually found a way to truly randomize the bit casing. So those guys found a way to actually truly randomize this thing. What do? They actually encrypt. Surprisingly enough. So this change will require a little bit of a key management, right? So you will create a key, a private key, or even a symmetric key, keep it hard-coded somewhere in the server, and you can do some key rotation. But this key, you take this key, and then whatever you received from the server, right? Like from the stub server, it's like, okay, IBM.com. Make it a canonical way, all lowercase. Have to be consistent. Okay, Hussein, you just lowercase it. That's predictable. We'll come to that. Take all that, encrypt it. And now if you encrypt it with the key, you're going to get a bunch of zeros and ones, zeros and zeros and one. And these are the randomization that will be used to casing. If it's 0 is upper, if it's 1 is lower. and so on. And that's what you get. Then you're gonna do this, you basically take that field now and then OR it with the original, whatever the user sent. And that you get a truly random one. Why do we do that? The way we do it, the way they did this is because they want this to be stateless even. Because once we get a response, remember, you gotta remember that the guy here, the stub resolver, which is us, sending the google.com, have no idea that it's gonna be changed, right? If I send google.com, I need to give back google.com. I don't need to give back my mixed casing. No, right? So what happens here, if I send this as normal, it's going to be mixed case right here only. But then how does the recursive DNS know how to flip back and match this to the original request? Eh? If you change it randomly, you got to remember how did you do it, right? It's like, oh, did I change the first one or the second one? You might say, okay, let's just take the transaction ID and then check it against the request we have. If it matches, then we're gonna do a lowercase all and then do a matching. Bad idea. That's the first thing I thought about it. No, you don't do that. This defeats the purpose, right? So what we need to do is actually use the same key and then do the same approach against that matching. So you're going to use the key, do the same encryption, and then do the matching. That is really a bulletproof way to get a clean resolution and very, very hard to predict, right? Because those guys, remember, the attacker mostly attack recursive DNS. They hardly attack these guys. They attack the 8888s and the 1111s, right? This is us. This is the router, right? And that's what's happening here, right? So all this mixed casing the attacker not only have to guess the ID, not only have to guess the source port, the source IP, the destination port, the destination IP, they also need to guess the ID itself, right? They also need to guess the casing of what the authoritative response actually responded with. And that just makes the guessing way exponentially harder. Here's how they show the actual numbers and everything. So yeah, I absolutely enjoyed reading this paper, and I think this is a clever way. Limitations, we're really adding encryption, right? So we're adding additional cost, and I don't know if there will be a DOS attack, denial of service, if an attacker found a way to guess the ID, right? But just try to flood the server with all possible combination of these things. The recursive DNS have to do this encryption for each one of them because the ID is a match, right? The ID is a match. And now this is an extra cost that the recursive DNS has to do that they didn't have to. That's, I think, a surface attack. I don't think they talked about this, right? But it's a possibility of an attack. That's the only thing I can think of, right? Because the attacker might just do random string changes, even with the goal to take down the recursive DNS. I don't know if it's feasible, to be honest. I'm not a security researcher, but that's one surface attack to me, I think. And that's it for me today. I thought I'd talk about this bits 20 encoding. Pretty cool paper. Let's thank the authors here. David Dagon from Georgia Institute of Technology, Manos Antokakis, again from Georgia Institute of Technology, Paul Vixie from Internet Systems Consortium, Tatsuya Jinmi from Internet System Consortium, Winky Lee, Georgia Institute of Technology. I don't see anyone from Google here in this paper, huh? But so let's shout out the original author here. Dagon, GA Tech. D. Dagon. Is this the same? Yep, David Dagon. That's the same guy. He used to work for GA Tech, which is, it's the same thing. Georgia Institute of Technology. It's been there for a while. But yeah, Google is actually implementing this now. They started slowly rolling this back, rolling this forward again. The only limitation here that they can think of is some authoritative name server might not reply with the correct one. So they have to have some fallback logic, right? Because that's the only limitation here, right? So they are slowly rolling this to the public, right? Again, will you ever sniff this or see it? I don't think so. If you do a sniff here, what you get back is whatever you sent. I don't think you're going to see those unless you're actually sniffing in the actual network publicly, right? Or you are an actual DNS recursive that implemented this thing. That's actually how I understood it, at least. All right, guys, that's it for me today. I'm going to see you in the next one. Goodbye.